So yes, first a brief history. So in 2002, there was a new faculty that was born at EPFL. It was life science. And it happened that I was in charge of a new class, an organic chemistry class. It was okay. A new organic chemistry class. And so I wanted maybe to make it a little bit different. So I wanted to have a lot of exercises, but also that the students are able to progress at their own speed. So that there is some self-learning, but also they get immediate feedback. I find it quite frustrating to have to wait for the correction, because if I understood, I want to go on something, another point, and not wait that there is some correction. And also this also allows to give actually more exercises than even the level of the exam, because somehow the best students, instead of getting bored because they solve all the exercises, well, they can do more. So I never gave actually the correction. And the idea was that the student know if it is correct or not. But if they cannot solve the problem, we try to have enough teaching assistants to help them individually. And so we had sometimes classes with 200 students and 10 teaching assistants in the same room. Of course, if we want to do this, especially with 200 students, it had to be online, no way to install software. And this happened in 2002. It was not obvious, but also if we want to have some perennity in the project, it's better that it's an open source project. So we tried Moodle. So it was in 2002, version 1.0.0. Moodle was a project that started in 1999. And yeah, we were one of the first ones to use Moodle. And we succeeded to use some Java applets, because I'm a chemist, so sometimes you need to draw some chemicals. So we succeeded to have a way to draw chemicals, but also we developed a Java applet that allows to visualize spectra, zoom in spectra, and allow students to solve the problems. So we spoke a little bit internally at EPFL, and a couple of years after, it became the Moodle.epfl.ch has been born. So I migrated all my exercises to this central platform. Now, if we think about e-learning, there is a kind of huge barrier between research and e-learning, because e-learning, you make multiple choice questionnaire. I never do this in research. And in research, I have some fancy program that make us 10,000 francs per license, and we cannot give this to students. So there is a problem there that actually we teach students stuff that we are not doing in research. And I was wondering how we can make some interactions between the e-learning and the research. And we started a huge development to create building blocks, a huge amount of JavaScript libraries, because we want that everything works in the browser, that are kind of fair, that can be found, that are reusable, that is relatively easy to maintain. And those little building blocks, because we are building all of them, they are interoperable. And what is a building block? Well, sometimes we had to reinvent the wheel. Sometimes we just had to create a small building block that allows to deal with matrices, to make the inversion of a matrix, multiplication, and so on. And this little building block actually had a big success, and there is over 80,000 downloads per week for these little building blocks. So some of the people are reusing those building blocks, and this is a way to maintain it and to keep it alive, to have some test cases and people use it. So it keeps the project alive. Now that's for everything that is processing those little building blocks, but we also had to create something for the front end, some graphical interface, so that we can create exercises for the students. And we developed a tool that allows to draw a couple of windows, allow those windows to interact between each other, and be able from those modules to access databases, to access tools that allow us to make prediction, calculation, or more and more to develop tools in JavaScript that are running in the browser. And we create modules, plenty of them. Everything in pure HTML5, we understood that Java was dead, definitely dead. But still, the students, some of them are on Linux, some of them are on Windows, macOS. The only way was that it works in HTML5, that you don't need installation, you don't waste time to ask the student to install something, they just go on a URL and they can use the tools. So the same tools is used for teaching, research, and to extract knowledge out of the data. And research, the same tool is today used on eln.epfl.ch, a lab notebook that is heavily used in chemistry, but I learned not only actually in chemistry at EPFL. So we create modules, and module may just be a grid with a background color, or a chart, or hierarchical clustering, and some interactive modules where you can display the result of a principal component analysis, or a molecule to display 3D structures, or maybe annotated charts or annotated spectra because you want to explain something to the students, or maybe simply a 3D scatter plot, or a mathematical function. So we create modules in order to create quickly and efficiently new applications. Of course, I'm a chemist, so there is also a module to draw a chemical, and it was also for life science. So we have also a module to draw a sequence of nucleotides or proteins and things like that. So a couple of examples, what we did with this infrastructure. And first example, I will teach you some mass spectrometry. And the idea of mass spectrometry is to measure the mass of a molecule, but in those molecules, some of the elements have different isotopes. So if you take chlorine, for example, well, there is 75% of chlorine 35, so it weighs 35, and 25% of chlorine 37. So this means that if you observe a mass spectrum of one chlorine, well, you will see this ratio 3:1 characteristic of a chlorine. And if I look at a bromine, well, bromine, it's very close to 50-50. Oops. So if we look at a mass spectrum of bromine, we are expected to see two peaks with the same height. Now it starts to be more complex when we have mixture of those elements. And if we have two chlorine, well, this is just mathematics, we can calculate this, but we will get this fancy ratio, if I remember well, it's 9:6:1, so you can recalculate this easily. Of course, this is super easy, just two chlorine. A real molecule has tens of atoms. So that's quite important to know for the students, because looking at the mass spec, they can directly say, oh, I have a chlorine in my molecule, or I have a bromine in my molecule. And one of the numerous things I teach them is how to find the molecular formula of an unknown molecule. And actually, they need to find out, oh, there is a bromine, I know it. So how we did this kind of, how did we solve this kind of problem? So we created a module that allows to make plenty of calculation that is called ChemCalc. This is back in before 2010 with Alain Borel that is now working in the Central Library. And the idea, and I'll skip this, the idea is to have this kind of exercise. I will zoom so that we can see something. Okay, so the student has a list of exercises to solve. So he has a corresponding spectrum. We can zoom in, check exactly the mass of the different peaks, check the relative height. And based on this, we tell him that this is an unknown composition based on carbon, sulfur, chlorine, and bromine. And so he can try, and maybe he thinks it's Cl Br, a chlorine and a bromine, it stays pink, so meaning it's not wrong. And continue to think, and it's Cl2, it becomes green, it means it's correct. It can go on the other axis. One of the problems is that you may wonder, but why it's not chlorine bromine? I was really convinced. So of course, he can do the calculation by hand, it may take time. But what we have here, it's a tool that allows him to calculate whatever he wants. So anytime he can say, no, but I was convinced it was bromine chlorine. Well, okay, just simulate it. Bromine chlorine would be this. So you can like that understand, and you can think about why it's wrong. Indeed, bromine would be a bigger contribution to this peak, but also the n+2 and things like that. So the idea is to offer to the students tools that allows to answer his questions. And without any hesitation, it doesn't have to call a teaching assistant. He can just try himself. And it also lowered the barrier because you're always afraid to ask a stupid question. Well, here, no, you just try. Nobody will know that you try something stupid or not stupid. Based on the same system, we did plenty of tools, and one of them has been published recently. In chemistry, old technique is infrared spectroscopy. That actually a molecule, it's a mass connected by springs, and the springs are bonds, but we have some characteristic vibration in a molecule. And we can distinguish around 6 kinds of vibration in the molecule. So we can teach this, we can show some fancy animation. A spectrum, the energy, that is the wave number, and we have some characteristic absorption. So in this case, we are expected to see 6 vibrations, and we indeed observe those 6 vibrations. But it's not interactive, so it's quite difficult to understand to the student, yeah, but okay, it's written CO stretching, okay, it's expected to be this vibration, but it's not very interactive. So we wanted to create a tool that allows the student to predict any molecule he wants. And so that's a publication that was done in the Journal of Chemical Education in 2022, so pretty new. We posted this publication on LinkedIn, and there were surprisingly a lot of feedback, in fact. Over 100,000 people saw this post. It has been over 2,000 comments, 2,000 reactions on this post. So we really see that something is missing where there is some interaction and the students can try by themselves. So how it works? Similar layout. The student can draw a molecule. We will send a request. We have a predicted spectrum. He can decide if he prefers absorbance or transmittance. But it's interactive. The student is able to click on a bond, and he will see the corresponding vibration. So based on, in this case, the 6 possible vibrations, when the system will show the more relevant vibration. Moreover, if he is on the spectrum, the student can click on a specific signal and he will see the corresponding vibration. Here it is an asymmetric vibration. This one would be a symmetric vibration. And if the student would like to compare two structures, he can edit the structure, ask for another simulation, and now we will get the superimposition of the 2 spectra, and we can start to discuss in chemistry the impact of a fluorine and mesomer inductive effect, mesomeric effect, and the effect on the wave number, and explain this shift. So it may be also a source of discussion to explain some basic phenomena we observe in organic chemistry. So based on this, the students will also have some exercises. So that's the kind of exercise they have. Those are experimental data. He will select an exercise, he will get a molecular formula, and based on the different absorptions and the different signals, the presence or the absence of signals, the student will have to find which chemical structure it is. So in this case, it is this one. If it is correct, it becomes green. Then do the next exercise. If they don't understand, they can simulate their mistake, they can simulate the molecule they thought would be correct and try to compare why it's not the correct result. We also focus a lot on nuclear magnetic resonance, and we did different publications in this field as well, and also learning, teaching NMR spectroscopy. So there is a specific website, nmr.cheminfo.org, where we will group all the tools we did related to NMR. Because it's super modular, well, we can put in one page so that the student can focus on learning NMR spectroscopy. We can put on one page all the relevant tools. So for example, here, if he wants to create a 3D model, in NMR, there is an effect that sometimes you want to know the distance. Well, the student will be able to, again, draw a molecule, put a sulfur there. I click on predict, and the system will predict a 3D model of the molecule. The student can then evaluate the distance. In NMR, sometimes we are interested in the distance. The student can click twice, and he will get immediately a distance. In a similar way, he can click twice, click once, click twice, and get an angle. So a lot of possibilities for the student. Something else he can do is to make exercises. Like for the infrared spectra, student will have a list of exercise. The student sees here a spectrum, and he will have to guess, based on this spectrum, the chemical structure. So in this case, this one. If the answer is not correct, and he doesn't understand why it's not correct, we have another tool. Like we did for infrared prediction, we have NMR prediction. And the student is able to predict any molecule he wants. He clicks, there is a prediction. This prediction is interactive, so the student can go over a peak and visualize in the molecule to which proton it belongs, but also to go over hydrogen in this molecule and see where should appear the signal in the spectrum. So we really promote the independence of the student. They can anytime test by themselves. So last slide, and I think up to now, even if eln.epfl.ch, it's using the same technology, we are not yet at the level where we replace applications. So in the browser today, we tend to replace applications, but we are not fully there yet. So this is a project that is done outside EPFL in collaboration with the German government, where we create an application for the processing of NMR spectra. But in this specific case, the goal is to process NMR spectra, meaning that researchers have the possibility, have all the tools here to process their spectra, to make auto peak picking, to zoom in, and okay, all what they need to make this kind of job. Even if this tool was designed from scratch to replace commercial applications or to replace applications that you have to install, we did a specific section we downgrade somehow this application for teaching. So in this case, we don't want to give all the tools to students because it doesn't make sense at a pedagogy point of view. But the students, based on the same technology, will have to process NMR spectra the same way we would do research. So they will have to make some integration. They will have to zoom and to process the spectrum like we would do. And it's the same application we use in research. And they will have to, here they get the unknown, the molecular formula of the unknown molecule. They may set the sum of the integrations and things like that. And at the end, if they know the corresponding chemical structure, well, they will be able to draw the chemical structure. In this case, it's this. Submit to the system, and if it is correct, the system tells it is correct, and they do another exercise. So what we are doing now is somehow changing the way we teach. We first develop an application for research, and we downgrade this application for teaching, while most of the time we were doing some specific tools for teaching. And yeah, I think this tool has also some impact on internet. Again, it's a real application, but it works from the browser. So no need to install. One click, the students are ready to do the exercises. And moreover, the teachers are able to create their own series of exercises. So some other universities will contribute so that we get more and more shared exercises that we can share between. That's all I wanted to show you today. So plenty of time for questions.